This lesson, entitled Solubility Equilibria, covers an application of equilibria where we're looking at how substances dissolve in water. Some key definitions from grade 11 that are important are that a solution is a homogeneous mixture with one or two more substances dissolved. And the key classification of solutions is that a saturated solution contains the maximum amount of solute dissolved at a given temperature for a given amount of solvent. Unsaturated has less than the maximum amount of solute, and a supersaturated solution has more than the maximum amount of solute. When we're dealing with solubility equilibria, we are studying saturated solutions, and the equilibrium reactions that we study and the constants are for a saturated solution. Now, last year you looked at the solubility rules, and we were studying equilibrium at that solubility at that point in a qualitative way. So we would look at whether or not a precipitate was formed given a particular combination of reactants. Now, this is still a very useful list, and it's one that needs to be memorized for the qualitative study of chemistry and for reactions. What we're going to be doing this year in our quantitative study is examining the fact that the precipitates from the solubility rules are actually what are referred to as slightly soluble salts. Because the reality is everything will have a certain amount of solubility in water. It's just a matter of how soluble it is. And the ones that are considered insoluble using this table have very low solubility, as you will investigate. Now, when we're looking at the equilibrium for a solubility equilibrium, what we are looking at is the salts that we're studying and how it dissolves in water. So this is the opposite of how we would consider reactions in grade 11. In grade 11, we would consider the double displacement reactions that led to the formation of the precipitate. So for example, in this first one, we might have had silver nitrate, which is soluble, reacting with sodium chloride, which is also soluble. And in the double displacement reaction, we produce AgCl, which is our precipitate, and the soluble sodium nitrate. So in grade 11, you examined these reactions and you created a net ionic equation. And the net ionic equation that you would have produced from this particular reaction is that AgCl is formed by the reaction of Ag plus and Cl minus. So when we're studying reactions qualitatively, this is how we would look at a precipitation reaction or forming a precipitate. When we're studying solubility equilibria, we are studying the solubility of a particular salt. So the ability of this salt to actually dissolve or break up into its ions in solution. So that's why we think of the equilibria as being the solid in equilibrium with the ions, so that we can imagine the solid going into solution. Now the equilibrium constant expression for this reaction is the concentration of Ag plus times the concentration of Cl minus. As you know, the solid, being a pure substance, is not included. And these equilibria are referred to as KSP, where SP stands for solubility product. So this is referred to as the solubility product constant. The reaction that you studied in the lab formed lead iodide. So when we're studying this equilibrium, we study the dissolving of lead iodide in water to form ions Pb2 plus and 2I minus. So when we're studying solubility equilibria, we need to be very mindful of the ratio of the ions in the solution because that will affect our KSP expression. So this is the concentration of Pb2 plus times the concentration of I minus squared. We need to apply the coefficient as we would in a regular equilibrium. As I mentioned before, it's important to recognize that this gives the relationship of the concentrations of the ions in a saturated solution. So when we have an equilibrium, we've got a saturated solution. Okay, so we've got the maximum amount of ions dissolved before we see a precipitate forming. Now, table 16.2 in your textbook gives you a list of the solubility products for some slightly soluble salts. What you'll notice is that the substances that are listed here are ones that the solubility rules would have led you to call insoluble in water. And if you look at the values of the KSPs, you'll notice that they're very, very small. So these are slightly soluble salts, and we're studying a very small quantity being able to dissolve in solution. Now, because the KSP represents the saturated solution, it is also a good indicator for whether or not a precipitate will form. Just like in our original equilibrium unit, we examined the expression Q. Okay, we called it the reaction quotient. In solubility equilibrium, we call this the trial ion product. Okay, so it's a product that we sub into when we don't know whether or not we're at equilibrium. So we call that Q. So if we're trying to decide if a precipitate's going to form, you'll see in the problems that we solve for Q, and then we compare the Q value that we've solved for to the KSP. If the Q is equal to the KSP, we've found a combination that leads to a saturated solution. If we have a Q that's greater than the KSP, we know that a precipitate will form. There are simply too many ions to stay in solution. And if the Q is less than the KSP, then no precipitate forms, or we're left with an unsaturated solution. A few other key terms: the difference between molar solubility and plane solubility. Molar solubility, when you're being asked for it, you're being asked for the mole per liter, the amount of moles of solute that can be dissolved in 1 liter of solution. And when we're talking about solubility, we're talking about a saturated solution. So it's maximum solubility. If you're just being asked for the solubility in grams per liter, that's the number of grams of solute that can be dissolved in 1 liter of saturated solution. Now, last year, you'll recall that you were looking at solubility curves, and you would have the solubility in grams per usually 100 milliliters, okay, on the y-axis, and then you would have the temperature in degrees Celsius. And you'll remember you did questions that asked you, there was several curves on it, and it asked you for various scenarios, whether it was a saturated, unsaturated, or supersaturated solution. And the values along the curve represented saturated solutions. Anything above was supersaturated, and anything below was unsaturated. So you were looking at solubility in grams per 100 milliliter. These two flow charts will help you to go between solubility and the KSP of the compound. So if you're given the solubility, this will help you to flow to the KSP of that compound. And if you're given the KSP, this will help you to flow to the solubility of the compound. And you might stop at molar solubility depending on the question that you're asked. The best thing